The swamps of Louisiana, the jungles of South America, the deserts of the Middle East, China's Tarim Basin, both shallow and deep waters of the world, and even the frozen tundra of the Arctic are home to GSI's seismic crews, who have from the very beginning made a practice of conquering hostile environments. The early GSI crews were pioneers, not just pioneering the new technology of reflection seismology, but pioneers operating in hostile corners of the world, places where simple survival was a mark of achievement, even more so when coupled with competent collection of valuable seismic data. GSI's professional personnel continue to exhibit the spirit of those early-day pioneers, working effectively and efficiently in many varying environments. Perhaps the most hostile environment for field crews is the Arctic, where temperatures double digits below zero are the norm, and temperatures as much as 60 below are not unknown. GSI began operations in extreme cold weather conditions in Canada during the 1930s. During those early years in the Arctic, simple survival consumed a large part of the time crews were able to spend on site. Only limited amounts of fuel and supplies were able to be kept on crew sites, and sometimes harsh weather conditions prevented the delivery of supplies when required. At such times, equipment had to be shut down to conserve fuel until the weather cleared and aircraft were used to replenish food and fuel. Years of Arctic experience have allowed GSI to become much more knowledgeable about operating in extreme cold weather conditions. Throughout this time, engineering teams have worked hand in hand with field operations personnel to help overcome the many data gathering problems caused by harsh weather conditions. The result is a supply of well-trained personnel, new equipment technology, survey automation techniques, advanced logistical support technology, and improved data collection and processing techniques. These innovations enable GSI to be consistent in acquiring large amounts of high-quality data in the short Arctic season. Due to the delicate nature of the Arctic ecology, land seismic operations cannot be carried out in the summer months when the tundra is thawed. Seismic operations used to begin in mid-November with the arrival of freeze-up and enough snow cover to allow heavy vehicle traffic. They normally continued through early May, depending on ground conditions. Now, the most productive time for seismic crews runs from January through May, about 4 months. Although operations sometimes start earlier, they are hampered during November and December by darkness and severe storms. Although land field operations are conducted through the winter on frozen tundra and the offshore ice pack, the work doesn't stop with the spring thaws. When the offshore ice pack has broken up and wind and thawing conditions have opened navigable areas in the Arctic waters, marine crews pick up where the land crews left off, performing surveys in both shallow and deep waters. The summer months are also busy ones for land personnel. The months of cold weather field operations are not possible without a multitude of plans and preparations during warm weather. Planning for the winter season starts in the early summer, only a short time after the close of winter operations. During the summer, all equipment is inspected and evaluated to determine what needs to be repaired or replaced. Repairs are carried out at this time to ready the equipment for the coming season. Summer planning includes both logistics and personnel. Fuel, food, and parts inventories must be planned, and vendors must be selected early enough to ensure sufficient supplies will be available for delivery to the crews when the winter season starts. Once plans are made and supplies are acquired, mobilization for the winter begins. Fuel and equipment are positioned at central staging areas for later distribution to the support facilities and crews. Before data collection operations can begin, survey control must be established, so the surveyors are the first members of the crew to arrive in the field. Survey control markers are set on the ground during the summer using a helicopter equipped with an inertial guidance system. Pre-positioning of the control markers allows immediate setup of the survey when winter operations begin. eliminating the slow, time-consuming drives across the snow and ice-covered tundra which would be required for establishing survey control once winter had set in. During the season, modern survey techniques are used for accurate positioning of station locations. The accuracy of positioning is checked with satellite translocation techniques. Salidas electronic navigation positioning is used along with conventional chaining to position the geophone locations accurately. As crews arrive in the field, equipment which has been used in other areas during the summer is returned to Alaska for winter operations. All modes of transportation, land, sea, and air, are used to bring this equipment to the field. A major effort is required to reactivate equipment which has been idle throughout the summer. Startup must be a coordinated effort and requires all personnel to be thoroughly familiar with the startup plan. Once the equipment is assembled at the crew sites, the vehicle diesel engines are started. Experience has shown that repeated shutdown of equipment in cold weather increases the incidence of engine failure, so the engines are run round the clock through the winter season, except for short shutdown periods for routine maintenance. The equipment used in the Arctic has come a long way since the first operations in the 30s. Energy sources, recording equipment, support equipment, all have undergone a transformation. In the beginning, dynamite was used exclusively as the energy source in both land and offshore operations. But GSI has introduced new source technology to help solve the data collection problems on land, at sea, and on the ice of the transition zone during winter operations. One energy source developed by GSI in answer to this challenge was the Thunder Wagon, which combined land and marine seismic technology to produce a piece of equipment peculiarly suited to meet the demands of the Arctic environment. The Thunder Wagon was designed to operate on Arctic ice, collecting data in areas where water depths are greater than 18 feet. This unique system used a cable designed on the same principles as a marine airgun streamer, but intended to be dragged over the surface of the ice. A Mayhew 1000 drill was used to make the holes which allowed the air guns to reach the water through the ice, and accurate positioning was maintained by satellite and mini-ranger survey positioning systems. To acquire data in water less than 18 feet deep, another source had to be designed and built. This source used an air gun integrated with a top drive drill. It was capable of drilling through the ice and positioning the air gun in the mud of the ocean floor or the bottom of a freshwater lake. These two sources were valuable in collecting data in the transition zone between land operations and the deep water of the Arctic Ocean. Additional design and experimentation efforts have yielded a single source, the vibrator, which is used in all areas of the Arctic. Wheeled vibrators are used on ice and flatland areas with small snowdrifts. In rougher terrain and deeper snow areas, tracked vibrators are used. These vibrators are also successfully used in the desert and any type of land area where a vehicle can maneuver. The newest product of GSI's vibrator technology is the X3 vibrator actuator system. In addition to being used on newly built vibrators, the X3 can be retrofitted onto any existing X2 30,000-pound force vibrator. The X3 increases vibrator peak output to 45,840 pounds and provides lower signal distortion at higher frequencies. The quality of vibrator performance is monitored by GSI's vibrator monitoring system. Individual vibrators are monitored continuously during operation, and a real-time report is produced which displays each vibrator's performance at the end of each vibration point. Crew daily operations are a delicately coordinated balance of activities. Surveying, drilling, recording, logistical support, and maintenance are conducted simultaneously, but on different segments of the prospect. Collection crews work 7 days a week and between 12 and 18 hours a day. They are highly mobile and rarely occupy a camp location for more than a few days. The camp is moved when the seismic crew has completed the portion of the program within easy access from the campsite. The camp is kept near the operation area to cut down on travel time and allow more field production time. Logistical support facilities operate 24 hours a day, ensuring that crew sites have adequate food, fuel, and supplies. The remote support facilities at Deadhorse and Umiat receive regular shipments from Anchorage by chartered aircraft. The ground crews unload the cargo of supplies and replacement inventory. The aircraft are then loaded with empty oil barrels and freight containers, along with equipment which cannot be repaired at the remote facilities for the trip back to Anchorage. Supplies from the remote support facilities are distributed to the crew sites in smaller aircraft, each equipped to land on the terrain at its destination. Where possible, land crews build airstrips on frozen lakes so larger aircraft can be used for resupply. Where lakes are few and airstrips impractical, smaller aircraft with ski landing gear land on the frozen tundra. The harsh working conditions and the long hours put in by crews take their toll on personnel. So the regular aircraft shuttles carry not only cargo but passengers, as personnel are rotated on a regular schedule to keep them at peak efficiency on site. Operations in the remote Arctic are more expensive than those in other parts of the United States by a factor of about 3 to 1, due to logistical problems and the cost of seasonal startup and shutdown. The startup costs associated with each new season and the daily operating costs are distributed over the total mileage of data collected during the season in calculating the cost per mile. The more mileage acquired during the season, the lower the cost per mile. Therefore, GSI makes every effort to keep both men and machines at peak operating efficiency for the most economical data collection possible. Part of this effort is GSI's continuing dedication to personnel safety, which helps to reduce downtime for crews. Regularly scheduled safety inspections and crew meetings are held to reinforce the importance and awareness of safety procedures and accident prevention. Individual crew members are assigned specific duties in the event an injury or accident does occur. Special precautions are taken to prevent fires, and camps and potential fire areas are equipped with fire alarms and extinguishers. Fuel transfer areas are provided with special high-performance fire extinguishers. Although costs are a definite consideration in seismic data collection, data quality is the prime concern for ensuring the success of any survey in providing the explorationist the means for finding hydrocarbon reserves. For these reasons, GSI is dedicated to delivering the highest quality seismic data in the most cost-effective manner possible. GSI has a commitment to conform to customer requirements without exception and to do it right the first time.